Hello. The subject of the presentation is implementation of an example of hierarchical Petri net, HPN, in LAD language in TIA portal. Petri nets are a convenient model for describing digital control systems, especially in the context of concurrent behavior. One of the varieties of interpreted Petri nets are hierarchical networks, HPN. The canonical form of hierarchical Petri net, HPN, extends the PN model to an ordered n-tuple, where P is a finite, non-empty set of places, T is a finite, non-empty set of transitions, S is a finite, non-empty set of signals, T, crossed out, is a discrete scale of time, chi is a hierarchical function, defining the set of direct subnets of given place, psi is a bivalent history function, assigning the history attribute to places. Lambda is a labeling function that assigns to the nodes expressions constructed on the elements of the set S. The transition label may comprise three components. Cond, created on the X and L sets and denoting the condition imposed on the transition, which is a logical expression generated using the logical operators not, or and. Abort, created in the same way like cond, but remaining in a different logical relation of the general condition of the transition permission, denoted graphically by preceding hash sign. Action, created on the Y and L sets and denoting actions related to transitions, graphically preceded by the slash character. Alpha is a start mark function that assigns in start place attribute to places, and places are graphically marked with the dot mark inside the circle representing the place. Epsilon is an end mark function that assigns an end place attribute to places. End places are graphically marked with the X sign inside the circle representing the place. Tau is a time function that assigns a number from a discrete time scale to the set of nodes n. Permission conditions T are 1. Each place connected with the transition T by the plane arc or with the permit arc must be active. 2. Every place connected with the transition T by the denying arc must not be active. 3. The weak condition cond imposed on the transition must be met. 4. If the start place of transition T has the hierarchy attribute, each end place of the transition must be active and the time action associated with it must be completed. 5. If a time action is associated with the start place of transition T, it must be completed. 6. The strong condition abort imposed on the transition T must be met. Actions related to the execution of the transition T. 1. Each start place of transition T is deactivated. 2. If the start place of transition T has the hierarchy attribute, each place in the associated subnetwork is deactivated. 3. Signals from the set S related to the start places of the transition T are deactivated. 4. If the start point of transition T has the hierarchy attribute, the signals from the set S related to the recently active places in the subnetwork associated with it are deactivated. 5. If there is a time action associated with the transition T, it is performed, and then all exit points of the T transition are activated. 6. If the exit point of the transition T has the hierarchy attribute and does not have the history attribute, there are activated all places marked as start places in the associated subnetwork. 7. If the exit point of transition T has the hierarchy attribute and has the history attribute, but not all the end places in the related subnetwork have been reached, there are activated all places that were active before its expropriation. 8. If the exit point of transition T has the hierarchy attribute and has the history attribute, and all end places in the related subnetwork have been reached, all starting points are activated. 9. Signals from the set S related to the exit points of the transition T are activated. 10. If the exit point of transition T has the hierarchy attribute, the signals from the set S related to the activated places in the related subnetwork are activated. 11. If there is an action associated with the transition T, the signals associated with this action are activated for one network synchronization cycle. A fragment of the network place is shown in figure. The main network, basic network or core network, consists of places marked as P1, MP1 and P2. The MP1 place is marked as a place with the hierarchy attribute, so it's a macro place. The associated subnetwork is presented on the right part of the figure. This subnetwork is only activated when the MP1 macro place in the main network is activated. Let's consider a situation where the place P1 is active and the input signal X1 has a logical value, true. In such a case the P1 place will be deactivated and the MP1 macro place will be activated. At the same time, the subnetwork associated with the MP1 macro place is activated. So the starting places of this subnetwork, the P3, P4 and P5 places receive activity. There are three separate processes in this subnetwork. Process 1, composed of nodes P3, T3 and P6. Process 2, composed of nodes P4, T4 and P7. Process 3, composed of nodes P5, T5, P8 and T6. Each of these processes can work independently of the others. In this subnetwork, two end places have also been distinguished, P6 and P7. Achieving activity by these places is a condition for allowing the execution of the T2 transition from the basic network. It is worth noting that these places are also places where processes 1 and 2 end. In process 3, its end place was not distinguished and was designed as cyclic process. After reaching the end places P6 and P7 in the subnetwork associated with the MP1 place, the MP1 place in the core network is deactivated and the P2 place is activated. At the same time, all places in the subnetwork are deactivated, the end places P6 and P7, as well as the currently active place from process 3, P5 or P8. The output signals Y1, Y2, and Y3 are associated with the sites P3, P4, and P8 of the subnetwork, respectively. They are to remain active for the duration of the activity of these places. If the macro place MP1 is inactive, neither of these signals should be active. Implementation of such a task with the use of Siemens TIA Portal PLC engineering software and LD ladder language is shown. The implementation must be carried out with regard to the operation of the HPN network. Each of the networks, including the core network, can be implemented as a separate function block FB with an associated data block DB. This will ensure the program code encapsulation and will allow to use such a program structure in numerous instances when needed. The figure shows the call of two function blocks mainnet and MP1net realizing the basic networks and the subnetwork associated with the MP1 macro place, respectively. Since only one input synchronization signal X1, associated with the transition T1, is distinguished in the basic network. The interface of the main net block has only one input signal of the same name and corresponding input signal has been assigned to it. Two additional signals from the main net block interface, MP1 end and MP1 enable, are signals that synchronize the cooperation of the basic network with the subnet contained in the MP1 net block. The same is the case with the MP1 net block. The interface comprises four input signals, X2, X3, X4 and X5 and three output signals, Y1, Y2 and Y3. Two additional signals from the MP1 net block interface, enable and end, are signals that synchronize the cooperation of the subnet with the basic network in the main net block. The connections are shown in the figure in text form. Figures show an implementation of particular elements of the basic network, implementation of both transitions, T1 upper branch and T2 lower branch. It is worth noting that the condition for the execution of the T2 transition is that the subnetwork associated with the macro place MP1 reaches all its end places, which will be signaled by the MP1 end signal, so this signal was used as a condition for performing the T2 transition. Allowing the execution of the operations of subnetwork associated with the macro place MP1 is realized in this block by the activation of the output signal MP1 enable. This slide presents an implementation of functionality of the FB2 block. The principle of operation is based on a simple internal automaton, consisting of three states, STINI, STWork and STEnd. If the automaton is in STINI state, after enabling the operation of the subnetwork, enable signal active, the state of the automaton is changed to STWork and all starting points of this subnet, P3, P4 and P5 are activated. Additionally, an example of T3 and T4 transition is shown. When all end places are reached, the internal machine state is changed to STEnd and the interblock sync output end is activated. Control of outputs assigned to the subnet can be implemented as shown for Y1. The figure also shows the moment of deactivation of internal sites of the subnetwork and transition of the control automaton to the initial state after the termination of the synchronizing signal from the basic network. Enable input. Next slide shows a modified version of the previous example, changed to impose on the T2 transition from the base network a strong, preemptive condition, which is intended to inactivate the MP1 macro place and thus deactivate its associated subnetwork without having to reach the end places therein. The implementation of such functionality can be similar to the presented above. The differences will consist in change of the condition for performing the transition T2 in the core network and on the need to deactivate all places from the subnetwork associated with the macro place MP1 without knowing which places were active. The conclusion that can be drawn is that extending the functionality of the MP1 net block by deactivating all places can cover both the presented cases of execution of the T2 transition, with and without expropriation. The history attribute gives us the ability to remember, freeze, the state of the subnetwork associated with a certain macro place at the time of its deactivation by expropriation and continue its operation from the saved state after restarting it. Let's consider the previous example modified by adding to the macro place the history parameter. The core network will obviously remain in the same shape and the subnetwork will require some changes in implementation. The internal code of subnetwork machine will be extended with an additional internal ST frozen state and it will be set at the moment of deactivating the macro place MP1, provided that not all subnet end places are reached beforehand. The condition of activation of the internal machine of the subnetwork must also be changed so that the subnetwork can resume its operation. The internal transitions of the subnetwork must also be subject to condition that the network remains in the STWork state. The figure presents an example for T3 transition. Similarly, the control of the outputs must be conditioned. Hierarchical Petri nets seem to be a convenient tool supporting the object-oriented description of the behavior of control systems. It is possible to easily implement the HPN in the ladder diagram language. Further work will focus on implementation of time dependencies in hierarchical networks, and resolving deadlock situations. Thank you for your attention.